morning, students. This is Dr. GVR Seshagiri Rao, Associate Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So today I want to discuss about theories of failure. So in this, these theories of failures are so very important while calculating, while determining failure conditions in mission design. So theories of failures are those theories which help us to determine the safe dimensions of a mission component. Okay, when it is subjected to stresses due to various loads and acting on it during its functionality. So whenever the component is subjected to some load, so definitely some stress. So suppose the object is subjected to tensile load, the tensile stress will occur. So, similarly, the compressive load, the compressive stresses, shear stresses, and subjected to torsional stresses also will occur due to various loads. Clear. So to avoid the failures, it's always have to take a safe design. Clear. So safe dimensions. So that's why here the theories of failures we are using to determine the safe dimensions of a mission component. So these theories of failures very important in design of the mission elements. It plays important role. Clear. So some theories derived. So important theories we will discuss now. So what are the theories we'll see. Some examples of such components are as follows. So the design components are IC engine crankshaft and shaft used in power transmission and the spindle of a screw jack. Clear. And the bolted and welded joints and ceiling fan rods. These are some examples only. So it may you can take the piston and the connecting rod and the crankshaft. Clear. And then clutches and the brakes. These all are mission components and design elements. The theories of failure play a key role in establishing the relationship between the stresses induced under combined loading conditions. And the combined loadings means, suppose sometimes the component subjected to the bending load only, and sometimes the component object is subjected to torsion load, and in other case is the combinedly the torsion as well as bending also will act on the component. So clear, these type of loads are called as the combined loads. So at the condition, the properties obtained from the tension test, like ultimate tensile strength and then yield strength. So whatever we have determined, we have calculated from the UTM. Clear. So these are standard tensile test values. Clear. These are, one is ultimate tensile strength and another one is yield strength. Clear. For establishing the theories of failure safe conditions, we will use these stresses. And the stress induced under combined loading conditions, that is a yielding stress and ultimate stress obtained using tension test, so which are called as theories of failure. So various theories of failures are there. One is the maximum principal stress theory, also known as Rankine's theory. Clear? The maximum principal stress theory, and then also called as Rankine. And the second one is maximum shear stress theory. It is also called as GUEST theory and Tresca's theory. And the third one is maximum principal strain theory. Clear? Also called as Saint Venant's theory. And the fourth one is total strain energy theory, HAIG'S theory, and the maximum distortion energy theory, VONMISES and HENCKY'S theory. So these theories are derived by using some experimental results. Okay. So in this, out of these theories, frequently we are using the maximum principal stress theory, Rankine's theory, and the shear stress theory, and then VONMISES and HENCKY'S theory. So all are important, but it depends upon the application. First one, we'll discuss about this maximum principal stress theory. So what is the safe condition for this maximum principal stress theory? Suppose if you want to design shaft by using this maximum principal stress theory. So you have to design a shaft means how to determine the safe dimensions of the shaft. What are the important dimensions of the shaft? The diameter. The diameter of the shaft is very important parameter in shaft. The length it may change. Okay. So that's why the condition. What is the condition for failure? The maximum principal stress is value, stress value and factor of safety always equal to 1. So what is the condition for safe design? The factor of safety greater than 1. Okay? The factor of safety value should be greater than 1 only. The condition for failure is these failure stresses and the factor of safety equal to 1. So to avoid failure, for safe dimension, you have to take the principal stress value and the principal value and factor of safety value always you have to take greater than 1. Clear? The maximum principal stress means less than or equal to permissible stress. Clear? So that where permissible stress is equal to failure stress by factor of safety. Clear? So this is the condition for maximum principal stress theory. The sigma 1, so it indicates maximum principal stress theory is less than or equal to the factor of safety. How do you calculate the factor of safety? Ultimate stress by the designed stress. So that is the ultimate stress is here ultimate stress, that is a yield stress. Clear? And here shown here factor of safety is here less than the greater than 1. This theory is not suitable ductile materials, suitable for these brittle materials only. Under loading conditions, triaxial or biaxial loading. Sometimes the component biaxially loaded and triaxial loading. Clear? So this is suitable for both conditions. Clear? Because the brittle materials are weak in tension. Clear? This is not suitable for the safe design of machine components made of ductile materials. Clear? Because ductile materials are weak in shear. So that's why the maximum principal stress theory always you can use for brittle materials only. But in some cases, this theory can be suitable for the safe design of machine components or made of ductile materials under following state of stress conditions only: uniaxial state of stress and biaxial state of stress condition. When principal stress are like in nature. Clear? So clearly mentioned here, absolute shear stress maximum is equal to half of the principal stress value. Okay. Under one more condition is there. Under hydrostatic stress condition, the shear stress in all the planes is 0. Whenever the component is subjected to that component also the ductile material is subjected to the loading. So under following stress conditions, what are they? One is uniaxial, biaxial, and hydrostatic. Then only you can use this maximum principal stress theory. Otherwise, you can't use. Clear? Next, the second one is maximum shear stress theory. What is the condition for failure? First, we will see condition for failure and what is the safe condition. Clear? The maximum shear stress induced at a critical under triaxial of the combined stress test is greater than the yield strength in shear under tensile test. Okay? The absolute shear maximum stress and under tensile test are this is equal to half of the yield stress. The condition for safe design is the maximum shear stress induced at a critical tensile point under triaxial load conditions or triaxial combined stress less than or equal to permissible shear stress. Always the maximum shear stress induced under critical tension test should be less than or equal to permissible shear stress. Yeah, the permissible shear stress you can calculate by using this relation. So what is the condition? The condition is shear maximum less than or equal to yield shear stress at a tensile test. For triaxial state of stress, So take the larger value of these three, sigma 1 minus sigma 2 by 2, and sigma 2 minus sigma 3 by 2, and sigma 3 minus sigma 1 by 2. So larger value. So which one is higher value? So take that value, and then that value should be less than or equal to this yield tensile stress yield upon factor of safety. This is equal to the 0.5 times of SYT. Clear? So larger of value. So for biaxial, this is for triaxial case, and for biaxial state condition, sigma 3 is 0. Why? Because here the loading condition is biaxially, two sides only, two directions. Clear? In first case triaxial, the loading load acting in three directions. In biaxial state, only two directions, x and y, either sigma 1 and sigma 2. Clear? The sigma 1, the principal stress value should be less than or equal to this sigma yt by n value, where when the sigma 1, sigma 2 are like in nature. Another condition is sigma 1 minus sigma 2 should be less than or equal to SYT by n when sigma 1 and sigma 2 are unlike in nature. Sigma 1 and sigma 2 are the principal stresses. Clear? The maximum principal stress and minimum principal stresses. This theory is suitable for ductile materials. Clear? So that is safe and so it gives safe design and uneconomic design. So these are the theories we have to use in the design of machine components. Okay, thank you. These are the references.
Like, share and subscribe. Hit the bell icon for more updates.